Hi, everybody. Good morning, and welcome to my talk about static application security testing. My goal here is to talk about static analysis tools and processes and how this basically pertains to the SDLCs in our respective jobs. My hope is that we can all come away with some tidbits on what works best for us. A lot of these stories are obviously based on my personal experiences, but I think we can all relate to a lot of what we're saying here. Quick intro about myself. I'm Sasi. I started out in AppSec as a researcher almost 10 years ago at this point. Spent a lot of time doing vulnerability deep dives and creating detection algorithms for dynamic and runtime analysis tools. And then also spent a little bit of time doing some DNS malware analysis. Finally moved into real world AppSec a little over 3 years ago. I'm currently involved in providing security advisory and process improvements for a large enterprise. So let's start with a quick introduction to static application security testing tools. So a lot of these tools have various techniques in which how they detect vulnerabilities. I did want to touch upon one of these techniques, which is data flow analysis. And this will be relevant as we go along the presentation. So data flow analysis is where one of the static analysis tools tries to understand how data flows through our source code. And this is done by emulating function calls. Obviously, it's not executing code, but it's going to assume that certain method calls are being called with a certain amount of data. And that way it can identify vulnerabilities. One of the techniques for doing data flow analysis is taint analysis. Now, taint analysis involves three different kinds of methods as part of the algorithm. First one is called a source method. A source method is where you have untrusted input entering your system. So a simple method like request.getParameter. This is exactly where an attacker would inject some sort of malicious value if he was attacking an application. The second type of method is called a sink. The sink is where the vulnerability would actually manifest itself. So let's say for SQL injection, this would be the actual data, the actual method that's going to call out to the database. Or for cross-site scripting, this would be a response.write, where untrusted inputs just coming back into the response. And finally, the last type of method is called a cleansing method. The cleansing method is where if there was untrusted input entering the system, this method would end up sanitizing those values. So again, for SQL injection, a standard parameterization function would be a cleansing method. For cross-site scripting, this would be a standard encoding method. And the way taint analysis now works is you introduce taint into the system at the source. You trace it through this data flow. If your taint reaches the sink before passing through a cleansing method, that would mean that that data flow is vulnerable because it never got sanitized. However, if it did encounter a cleansing method, then we can say that it's a safe data flow. So classic advantages of SAST, to take a quick overview. The biggest claim is that you're shifting left. We do want to find vulnerabilities as early as possible in our SDLC. Static analysis has also been around for a while, which means there are a bunch of tools, established processes, various people giving talks about static application testing. And so there's just well-defined methodologies of how they can be integrated into our build pipelines and identifying issues as early as possible. However, if you've ever had the unfortunate opportunity of triaging static analysis tool results, you would know that the biggest problem is the sheer number of false positives that we see. And this isn't to blame the technology itself. The technology is built with the assumption of finding as much as possible. This is just built into the SAST philosophy. But there are multiple reasons why this is the case. Most common ones, definitely not an exhaustive list here, but unknown cleansing functions where your engineering team maybe has their own custom methods for encoding values or making things safe or validating inputs based on your application's context. And a standard SaaS tool isn't going to know about these. Sources and sinks where a tool might assume that certain methods are valid sources or sinks. However, your application might be built a certain way where certain sources may not make sense, which means an entire data flow can be excluded from your taint analysis. And with modern language constructs coming in, it just gets really hard for tools to keep up. You might have languages that perform dynamic code injection, or you could have annotations, you could have firmware or some sort of middleware that's just not going to show up in your data flow. And these are just going to be like gaps for the static analysis tool to really understand what's going on in your code. So that brings us to my proposed methodology. My goal here is not to really come up with the next new technique for static analysis, but rather let's see what's available today and how can we then bring this into existing processes in our SDLC to just better leverage all these static analysis tools. So the first step is the most obvious step. Start small. It's really tempting to just throw an entire repository at a static tool, hit go, and then look at the number of results that's going to come back. It's rather, you don't want to take a more methodical approach. Start with really small number of vulnerabilities, maybe just the high value ones. Maybe there are a couple of issues that are more relevant to your application. You just care about cross-site scriptings, or you just care about XXCs and SSRFs, whatever it may be, but just start as small as possible. Next, verify your data flows. Since you are starting small, hopefully it's easier to do a few spot checks, but look out for those pitfalls that we just mentioned. Is your application defining annotations or middleware classes or external dependencies that are injecting code in some way, shape, or form? Just having an idea of how the application is working would help identify those gaps. Also, are there any custom validation or sanitization functions, as we discussed before? In general, as a security team, we all benefit from having some sort of an inventory of security controls that our applications are using. So this might actually end up being a nice side effect of this effort, where you actually collect all these sanitization methods, which may or may not actually be effective. So it just acts as a nice perk here. Next one is to triage with purpose. The reason I specifically call this out is you do want to have a proper system for how you're prioritizing the results. Because even by starting small, you could be dealing with hundreds or even thousands of issues, depending on the size of your repository. So start with prioritizing based on any number of criteria that's relevant to you. Again, it could be based on the severity of the findings that your tool is offering. It could be based on certain types of vulnerabilities that you care about. Whatever it may be, just try to create a method to the madness before really diving into it. And then we come to one of the interesting parts here, which is creating custom rules. Most static tools out there, regardless of whether they are proprietary or open source, do offer a way to create your own set of rules. They don't have to be new techniques for static analysis, but rather helping taint analysis in a way that they understand your application's context. Do you have custom cleansing functions? You can define those. Do you have additional sources and sinks, or you want to remove certain sources and sinks? You should be able to define these using these custom rules. So I'm going to give a couple of use cases here based on how custom rules basically help me in my job. First one we're going to touch upon is open redirect or unvalidated redirect. So very straightforward vulnerability. Obviously, we're looking for redirects in the application that shouldn't be happening without any validation. In the example I have here, we did have an application that we were evaluating. And in the first line, you can see that there was a query parameter that was accepting a URL. So anybody could basically provide any URL. However, the way the redirect was constructed was that the domain part of that URL was hard-coded. And as you can see in that example, it's pulling it out of some context, which is hard-coded into the application. So even if you do provide an absolute URL in the query parameter, the redirect is going to be unsuccessful. You could not get out of the domain. And we saw hundreds and hundreds of false positives because of this coding pattern that developers were just using across the board in this application. So how do we create a custom rule to help us basically negate all these false positives and just find the actual issues? So the way we dealt with this is, even though response.redirect is a sink from a data flow analysis perspective, we decided to assume it was a cleansing function if and only if the argument inside the redirect method was actually a concatenation of multiple values. And the first value of that concatenated string was always a constant. Now, I'm really oversimplifying this. There can be more nuances added here. You could be looking for the exact variable of that constant that's being ingrained in there. You could be looking for a type to say that that is actually a string. You can even look for exact values of what you're looking for. But just giving this idea of the fact that there is going to be a domain at the start of the string, does increase the idea that yes, we can trust that if there is a constant at the start, this would mean that we are now looking at a validated redirect, basically. The result of this was that we were able to remove hundreds of false positives out of the result. But more importantly, this kind of cleared the fog out, and we were now able to clearly look at more than 50 true positives that just stood straight out of the scan result, right? So yes, there is a little bit of investment here to be able to get to this point, but now that we have it, we don't have to go back and triage more false positives. Any new issue that comes in is most likely a true positive from this project. The next use case I'd like to talk about is SQL injection. Again, straightforward vulnerability. Hopefully, we don't have it in most of our applications. However, unfortunately, I do see this from time to time. So this was, again, a case where I was looking at this application. It was dealing with concatenated SQL queries that was being called through the execute SQL method. So yes, it definitely looks vulnerable. The static tool did the right thing by calling this out. However, on closer examination, we found that some of these queries weren't even accepting user inputs. They were just queries with a bunch of constants in them. And so we started seeing a lot of these false positives. So we wanted to dig in to understand what is exactly happening. Now, the data access layer on the application offered two methods for executing SQL, as you can see in the examples here. The first method accepts a SQL string and accepts a list of parameters. And the implementation of that method was basically parameterizing the query before calling the database. However, the second version of it was just accepting a string and calling the first method with an empty list of parameters. So we ended up seeing that there was a pattern where developers were just copying the usage of the second method, and they were concatenating queries and sending them through. Some of them, unfortunately, did have user inputs, but majority of them did not, which means we were, again, dealing with a bunch of noise and not able to get to the actual holy grail, which is the vulnerable results. So what did we do here? There are multiple ways where you can address this. The first thing is you do want to improve security, improve accuracy. So making sure that you have established sources for the SQL queries. What do you define as sources where user inputs are coming in from? So the query parameters, as we discussed, making sure second order SQL injection is taken into consideration, as well as flagging data flows where execute SQL was being called without parameters. So the way we ended up doing this is we decided to leverage what developers call design patterns. Most reasonably mature dev teams do end up developing a certain set of design patterns. They might not have them officially documented. More mature teams typically do. But the idea is that development teams would expect certain coding practices as part of their everyday job. And this is what they use during their peer reviews, and they have this agreement. So from the security team, we decided to leverage the existing design patterns that they already have and introduce a new pattern for the sake of security. The idea was to rewrite the data access layer in a way that will enforce the usage of parameters, regardless of whether you have parameters or not. So what that means is that the new API on the data access layer now just has one call for execute SQL, which has the SQL query and a list of parameters. There was no way to circumvent the list of parameters. So what happens when you have a real reason where you don't have parameters to send in, you would send in null. So how does this help us? What we ended up doing was we created a custom rule now that just catches calls to execute SQL with a null list of parameters. So does this result in false positives? Of course. But the number of false positives is greatly reduced. So now our team just gets notified every time there is a call to execute SQL with a null. It takes a security engineer a quick glance to identify if that's truly a false positive, or if it's a case where the developer shouldn't have passed null and he should have used parameterized list of queries. This is just one of the ways in which you could solve this problem. This is a slightly more complicated problem than the open redirect, but this was kind of the approach that we ended up taking. But the most important one here is the fact that design patterns can really help. One thing I do want to call out is that static analysis tools are just one part of the puzzle. Anytime we're thinking of a problem from security perspective, we do want to think of people, process, and technology. So the technology aspect is solved by the tools. But we also want to look at areas where you can leverage people and process, because that's when you end up coming up with a full-fledged solution that can scale over time across all your teams. And the last step in this overall process is just doing this over and over again. As you can remember, we started small. We're here with a reasonable baseline. We're going to go back, expand the number of vulnerabilities, expand the categories until we're done. The most important part of this exercise is actually not this iteration, but the end result of it. We want to come to a baseline that brings us to a point where we're comfortable that we have reviewed everything that we wanted to review at the start. Maybe it's just a list of criticals, that's just a list of highs, just a list of 10 categories or OWASP top 10, whatever it may be. Because once you have this baseline, now you're at a point where every new release of this application is going to give you a new set of findings that you need to review, but it's going to be a really small subset rather than reviewing an entire repo with hundreds of thousands or maybe even tens of thousands of issues, depending on the size of the project, right? So the real value in actually implementing static analysis as part of your SDLC is not in the scans, but in the baseline and what you do after you create your baseline. So this was all great. We were able to really, if this really works, awesome. In reality, we know that's not true, right? Security teams are always struggling to keep up with the number of findings that are coming from a number of tools and data sources that we have available. Static analysis is just one of the pieces in that puzzle. So does it really help us do our job better? Let's take a quick look at a typical static analysis testing cycle to understand this, right? So I'm just giving a couple of examples. I'm pretty sure this isn't exhaustive, but the first model I'm thinking of is where you're committing code to a branch, or developers are committing code to a branch. You have a pull request created. Hopefully they're not committing directly to the main branch. A bunch of folks go in, give some peer reviews. The pull request is finally merged to the main branch. As soon as the merge happens, it triggers a static analysis scan because it's built into your build pipeline. And then you have the results come in and you can start reviewing them. That's one typical model. The other one, maybe you have a very large repository, it's too expensive or just too long to be triggering scans for every single pull request. In those cases, you would just have a scheduled scan, right? Maybe you're pulling from main branch, you're scanning it once a day, once a week, once a month, whatever it may be, depending on what's most convenient. And then eventually you can still review the results, file bugs, and make sure that everything is valid. However, in reality, what happens is that the product actually gets released before we as a security team go in to review the scan results. So sure, we were able to shift left in scanning our code, but we really couldn't review the results. So did we effectively shift left here? Because we're still finding those issues after release. It's as good as doing a pen test at the end of it, or any other security control you have at production time, not at build time. So what can we do about this? Can we shift left any further than where we are with static analysis? This brings us to a concept of proactive scanning. Proactive scanning has been catching up for a while. The idea behind this is quick time to results from static analysis tools. And when we see quick, we have two different contexts here. One is quick in terms of the speed of the scan. The scan itself has to be as fast as possible, typically seconds, if not minutes, but not more than that. And then quick in terms of as early as possible in the SDLC. And when we say early, even build time is not early enough. We want to be there at development time. The most important thing here is that we need to be in the same context that the developer is in. Because typically when we find vulnerabilities after the developer is done with a feature, they're done, they've moved on to another project. So to come back, get that context of what was going on to be able to identify the fix for whatever bug they filed, it does take there's a cost associated with it. So we do want to be in the context of the development. So now let's see how proactive scanning changes that pipeline that we were talking about. So as usual, developers are going to commit code to a branch, create the pull request. But as soon as the pull request is created, you have a static scan running on the pull request. And now you have the results from the pull request, which means it's still in the context of the developer itself. They can change the pull request immediately with the fix. You can do a remediation scan immediately because we mentioned that the scan has to be really fast. Once we know that the fix is in, then we merge to main. So here we have truly shifted left because any code that goes into main, we assume, is safe enough. Obviously, it's not going to be an exhaustive list of issues that we can find, but at least things that we can identify and things that are very important for us to identify this early, we should be able to do that at this point. This brings us to an interesting question. Is this the most we can shift left, right? We're talking about pull request here. Can we shift even further left? What about scanning the feature branch even before the pull request is created? Or maybe even further left? What about identifying bugs at the IDE when the developer is literally creating the vulnerability for the first time, right? Couple of challenges there. With the feature branch, one of the things is different development teams use different branching strategies. You could have a feature branch, you could have another branch from that feature branch, you could have independent developers having their own branches that merge to a feature branch. There's a ton of ways to do this, right? And as a security team, we don't want to be dealing with all of these methodologies, keeping corner cases into consideration and so on. It just doesn't help us with the coverage itself of these issues. And at an IDE level, there are actually tools that help us do this. There are vendors that offer IDE plugins that can be installed. But again, it means that we're chasing developers, making sure that they are installing these plugins, keeping them updated, they're using them the right way, and so on. So pull request, I believe, is a reasonable compromise where it's early enough, but it's still at a central point where, as a security team, we have a certain amount of control over a single point. So regardless of what branching methodology you use, you do eventually have to come into the main branch. So having that level of confidence seems to be a reasonable compromise at this point. There's one caveat I want to bring up with respect to static analysis. We've been talking about data flow analysis all this time, but that's just one type of rule. So with pull request, if you think about how data flow analysis would work, we typically don't have access to the entire data flow, right? If the pull request is a brand new feature that has all the new files with the source and sync and everything involved in there, sure, we should be able to do a reasonable amount of analysis there. But what happens if it's a change to an existing feature, right? You could have just the source in the pull request, but the sync might already be in the code, right? So it's not in the PR anymore. Or you won't see the sources and syncs, but you might be introducing a new cleansing method or invalidating an existing cleansing method by mistake, right? These are not going to be caught by data flow analysis on a PR because you just don't have enough code in there. So there's another type of rule called a structural rule. All the structural rule does is it verifies the semantics of the code that you have at hand. It could be a single line of code, it could be an entire method, it could be an entire class, it could be pieces of code. But your rules would define these semantics, and you should be able to run these semantics on these semantic rules on your PR. It's not going to be exhaustive, obviously. It's not going to be it's not going to be able to cover a lot of the vulnerabilities that data flow analysis would cover, but it does help with those initial goals we were talking about, which is fast scans and fast time to resolve. So some of these low-hanging fruits that might get missed or just lost in oversight, we should be able to catch them with proactive scanning with structural rules. So let's take a quick example of what I mean here. So I know I can't see you guys here, but I'm pretty sure you're cringing when you see grep. So grep is a tool that all of us use, developers and security folks alike. Security, especially if we want to take a quick look at what something's happening in a code that we are new to, we would just run a grep to look for a specific method call or a pattern, right? If you are a team that literally has no static analysis tool at all in your build pipeline, at least grep is a good start, right? It's not the best option, but it is super simple to get started in. I'm going to be using a single example across the next couple of slides here, which is looking for insecure connections established from your code. So we do want to ensure that any TLS connection starts with TLS 1.2 or 3, or sorry, 1.2 or 1.3, not anything below that. So that's the goal of these rules here. So I just have an example here. It's looking for Java files because this was a Java example. And it's basically saying, hey, if you're not using TLS 1.2 or 1.3, report this. It's not the perfect rule. It's going to have some false positives because it's going to be reviewing comments as well. But at least we have a start. PMD is a more established open source static analysis tool. It's been around for a while. It supports multiple languages. It does have a few out-of-the-box rules, but it also allows you to create your own custom rules. And what's even cooler is that it allows you to define your own custom language. So if you have proprietary languages developed on XML, YAML, JSON, whatever it may be, you can actually define these languages in PMD and then create custom rules to find vulnerabilities on your proprietary language, which is awesome. So what PMD does internally is it creates this data structure called an abstract syntax tree, the AST. The AST is just a tree structure, and you should be able to traverse this tree, this structure to look for vulnerabilities. You can do structural analysis in a straightforward way. In the future, you can also do data flow analysis. There are ways, because all you're doing is you're just traversing the tree. So I have an example here. This is a structural rule, again, for the same thing. It's looking for SSL context.get instance in the Java code, and it's looking for cases where you're not using TLS 1.2 or 1.3. So the rule does look a little complicated than grep, obviously, but the nice thing is PMD also offers what they call a rule designer that actually parses out any sample code that you can provide, and it gives you the AST structure. So you don't have to actually remember all that constructs in that rule. It's pretty straightforward to write the rule. The last tool I want to touch upon here is Semgrep. This is short for semantic grep. It's been around for a while, but now it's actively maintained by R2C. It is basically a glorified version of grep. So you're still doing searches on your code. However, it does have some understanding of the semantics of the language you're scanning. So it will exclude comments and so on, and it is trying to look at executable code as much as possible. The rule patterns here are, again, very straightforward. You're just creating like grep style patterns to look for things that do or don't exist. So as you can see, I have an example here where it's looking for, again, SSL context.get instance, but it should not have TLS 1.2 or 1.3 in the arguments in there. So they have a few straightforward examples on their website, but there's also a nice community where you can get some more custom rules or even develop your own top of it. And the nice thing is it's really fast. So what am I trying to say in conclusion? So static analysis tools have evolved over the years. They've come a long way. My goal here in talking about the last three open source tools is not a comparison between the three, but just a starting point for what's available out there. It is by no means an exhaustive list. There are a ton of proprietary and open source tools out there that you can use. There are multiple ways to get started. So I'm hoping that what I offered here gives you something to start off if you're new to static analysis, or if you already have some good tools and processes, hopefully this will help you mature into a better process over time. But regardless of everything said and done, the best process that you can roll out in your organization is the one that fits your SDLC. It doesn't matter how many tools, how many vendors are out there. No one can claim that they have the best option that fits your needs. That's up to you to decide. So what's best for your team's culture? What's best for your engagement with the engineering teams? Where do you really want that feedback between developers and between your tools and how your build pipeline is set up? All that matters in finally deciding the right tool and the right process, the one that fits your SDLC. Thank you for the opportunity. Feel free to share your experiences on Twitter, and I'm around if you need, if you have questions. Thank you.